Okay, hello everyone. I had some requests through email to do a few problems from the review. So I'm going to go through those and then we'll post this to the YouTube channel, obviously for you guys to watch. So I've highlighted the ones that were requested. Excuse me. So it says how much money should be invested today, this is number 6, in order to have 15,000. So that's a future goal in 10 years. So that's a timeline. If our rate is, okay, so we have 3 parts here, 5% compounded monthly. That would mean that 0.05, because we have to use the decimal, is our R, and N is 12, because we're compounding 12 times per year. So this is the formula, knowing the difference between which two formulas to use. If you're compounding for a certain amount of time, you use this formula for compound interest. And if you're compounding continuously, we use the variable P, then we use the number E to the RT power. Remember, that's the PERT formula. This one's only if you're doing continuously. So that's going to be for part B. So let's plug in what we know. So we want to have 15,000. That's our future value. So we don't know how much we're going to plug in. We have 1 plus 0.05 divided by 12 times a year, all to the 12 times a year times 10 years. So this exponent is 120. Sometimes I go ahead and figure that out. It just makes typing in the formula a little bit quicker. So, and let's talk about how to type this in. First of all, this is not solved for the correct letter. We would want to solve it so that P is by itself. That makes it easier to type in what you're going to solve on the calculator. So if I solve this, I would divide over that big parentheses. So it would be 15,000 divided by the 1 plus 0.05 divided by 12, all to the 120th power. So I'm going to carefully enter that into my calculator, 15,000 divided by, I always put a parentheses on anything in a denominator, 1 plus 0.05 divided by 12 raised to the 120th power. It looks like we need 9,107.42 cents, so $9,107.42 if we want to have 15,000 in 10 years. So the P is approximately 9,107.42. So that would be part A. I'm going to do part B, and then I'm going to leave C as one you can try on your own and check. Continuously means we're going to use the PERT formula, so 15,000 is still my initial goal that I want for the future. I don't know how much I'm going to invest today, and then I have E is a number, and then it's 0.05 again because the rate is still 0.05, and the time is still 10 years. So that actually makes this decimal exponent 0.5 if you multiply that out. So this is 15,000 divided by E to the 0.5 is P. So 15,000 divided by, and I believe on mine I have to enter the exponent first. This is not typical. Most calculators will let you enter in. Oh, it didn't like that. It did it twice. So 15,000 divided by, clear it out. 15,000 divided by 0.5 and hopefully just E once. Yeah. And then hit enter and 9,097.96. So P is approximately 9,097.96. Now I'm going to leave you guys to do the last one. This would be 0.04 as the rate though, and compounded quarterly means 4 times a year. So N would be 4. And this one should be done similarly to part A since it's not continuous. Okay, let's look at the next question I received, which was number 7. We're practicing writing these as single logs or breaking them up. If you're going to go to a single log, you have to put all the powers back on first. So any coefficient out front goes back as a power. That's one of our log properties. So this will be log x squared minus log of the argument, which is x squared y to the 8th, all to the 1/2 power, plus log z to the 3rd power. You can apply this exponent rule here, so you can take half of each of those by multiplying 8 by a half and 2 by a half. That'll then actually take care of the radical part for you. So this would just be x and y to the 4th as my argument, and then plus log z to the 3rd. Now we talked about in class that anything that's subtraction ends up in the denominator, anything that has a positive out front ends up in the numerator. So my final answer here should be log big parentheses with a denominator. This xy to the 4th will be in the bottom. The x squared was a positive log out front, and the z cubed was also a positive log out front. And they want us to notice that the x and the x squared can reduce. So my final answer actually would be log of xz cubed over y to the 4th. Okay, so for B part, we're supposed to break this log back up into multiple logs that are added or subtracted together. We've got this big cube root here, so we're going to have to take care of that. Let's see, where do I want to start? Yeah, I'm going to start with that. So that would be log of y to the 5th, x to the 4th, y to the 6th, all to the 1/3 power. I could then apply the 1/3 power to all the powers inside. So that would be y to the 5/3, x to the 4/3, and this would actually be y to the 2nd, because 6 divided by 3 would be 2. We could then break this up into adding or subtracting, or we could leave this as 6 over 3 for a second, because we do have y's we could reduce out. In fact, I could have done that here. So let's back up for a second. Sometimes when you get into a problem, you realize that if you do something else first, it makes the problem easier. We could reduce this y5th and y6 first, since there's no adding or subtracting. That would leave me with a 1 on top, and this would just be a 1 down here. So that makes this guy, before I apply the power, a 1 over x to the 4th y to the 1/3. Okay, so that's a little bit easier to deal with. So we have log of 1 to the 1/3, because that's a top number, minus log of x to the 4/3, because that's getting that 1/3 power as well. And this is also on the bottom, so minus log of y to the 1/3. Okay, so now we have to talk about, for a minute, what does this guy actually equal? Because we don't usually have an argument inside that's a number like that, like the number 1. Anytime you have a number 1 inside, this is base 10. 10 to what power equals 1? I can pull the 1/3 to the front, and in fact, I could do that, but just what you're going to realize here is that anything to a power that equals 1 inside is actually equal to 0. So this guy is actually 0 right here. It's going to go away. So this right here would be a negative 4/3 pulled to the front log of x, and a negative 1/3 log of y. So that would be the final answer for that one. All right, for part C, we have to first distribute the 1/3 that's out front of the bracket. Make this a little bit easier to deal with. That would be 1/3 natural log of x plus 1. 1/3 of 3 would be just 1 out front, so natural log of x minus 2. And this is minus 4 natural log of x because it was not inside the bracket. We put all powers back on using the property. So this would be natural log of x plus 1 to the 1/3 power, plus natural log of x minus 2 minus natural log of x to the 4th power. Anything that's positive will end up on top. Any logs that are negative will end up in the bottom. So this is natural log of the cubed root of x plus 1, because remember this power is actually a cubed root, times x minus 2, because this is also going to be on top, and plus turns into times, all over the x to the fourth. So that is the answer for part C. For number 8, we have a couple different types of equations to solve. If you can get powers to match, or bases to match, we can set powers equal. So this would be 3 to the x plus 1, and 27 would be rewritten as 3 cubed to the negative 2x. We have two powers on the same base, so we multiply the powers. So that's 3 to the negative 6x. And because the base is the same and we have one on each side, we can now set the powers equal to each other and solve. So I'd subtract that x over, divide by negative 7. So the answer to A part is negative 1/7. Similar for B, you have to get everything to be to the fourth base because everything can be converted to 4. So anytime you have something in a denominator, you want to move it up and change the sign of the exponent. So this would be 4 to the negative 1, but it still has the x plus 6 on the outside as a power. And 4 to the third power is 64. So then next we have to distribute this negative 1 and this positive 3. So we have 4 to the x times 4 to the negative x minus 6 equals 4 to the 6x plus 24. Excuse me. So then we would have okay, so we're almost there, but you can't have two bases on the same side. So we have the same base, so we add their powers. So it's still base 4, but it would be x plus negative x, which is no x's, so it's just going to be negative 6. And then we set the powers equal. I would subtract over the 24, so this is negative 30 equals 6x, or x equals negative 5. Okay, now we're going to get into the ones where you can't solve these using the power rule, or the base rule that we just went over. None of these can be made to have the same base. This guy right here, the first thing I would try to do is at least try to isolate the one that has the exponent on it. So this is 3 to the x plus 2. And these are both divisible by 5. 85 divided by 5 is 17. So that would be 17 over 2. And obviously 3 and 17 over 2 are never going to be the same base. If this happens, you need to apply a log because you have a variable in an exponent and you can't get rid of the bases. So that means we have to use the log so that we can pull that power to the front. So we have log of 3 to the x plus 2 power equals log of 17 over 2. Now we can pull this power to the front. So this would be x plus 2 times log 3, and that is going to get distributed, equals log of 17 over 2. Distribute the log 3 to both of these, so x log 3 plus 2 log 3 equals log of 17 over 2. We would subtract over the 2 log 3. And then now we're going to divide everything by log 3 to get the x by itself. Excuse me. So this is log of 17 over 2. If you want, you could put the 2 back on that power. So that would be minus log of 3 squared. So that would be 9 over log 3. And I'm fine with this on a test situation, but if you wanted to go even more in detail, you could then combine this subtraction into a division. So on top I would have 17 over 2 divided by 9, which I can fix in a minute, all over log of 3. 17 over 2 divided by 9 is really times 1 over 9. So that's 17 over 18. So that top fraction will reduce to 17 over 18 over log of 3. And because these have the same base, they're both base 10 because they're both regular common logs, you can turn this back into a single log by writing the top part as the argument and the bottom part as the base. That's using the change of base formula backwards. So that is a more simplified version of this answer up here. Both of these are considered exact answers because we haven't rounded anything. If you wanted to get an approximation, obviously you need to type in something into your calculator. And normally it would be either this version or this version that you would type in. You wouldn't be able to type this in since it has a base 3. I'm going to do D on its own thing later. In fact, I'm going to do maybe a different version of D so you can practice this one. Remember, this one was related to the bonus question. So I'll be posting a separate video just for that. And let's look at a couple more of these. The rest of the equations in this problem were all related to logs. So we have log equations. There's 2 types. If you have a log on each side that matches base-wise and there's 1 on each side, you can just say set the insides equal. So in this case, we would solve 5x plus 9 equals 3x minus 17. So that would be 2x equals negative 26. Divide by 2, you get negative 13. Let me make sure I didn't miss any signs. Yeah, because we would subtract the 9 over and we would subtract the 3 over. Now, you have to check this because every argument of any log has to stay greater than 0. 5 times negative 13 plus 9 is not greater than 0, and neither is this one if we plug it in. That means the solution doesn't work, so this would be no solution. So you have to check with logs because they have domain restrictions. Okay, so you have to be careful there. So this next one, you notice that there is something else in the problem besides just logs. Anytime you, let me highlight this, anytime you have a log equation and there's something that doesn't have a log attached to it, you cannot just drop the logs and solve anything. What you have to do is get the logs on one side and then get everything else on the other side and try to turn it into an exponential. So I'm going to add this over. So this would be log 2 of x plus 3 plus log base 2 of x plus 7 equals 5. This is plus, which means we can turn this into a multiplication single log, still base 2. X plus 3 times x plus 7, that's my new argument. I could then FOIL that out, so this would be log 2 of x squared, 3x and 7x makes 10x, 3 times 7 is 21, equals this. You do not set the trinomial equal to 5. This has not got a log. So you have to convert this to an exponential. So this is 2 to the 5th power equals the trinomial. So 2 to the 5th is 32. And since we have a quadratic, I'm going to subtract the 32 over. So I get x squared plus 10x minus 11 equals 0. Factor that into x plus 11 and x minus 1. Solve those, we get negative 11 and positive 1. You have to check them both. So we need to check to make sure that our arguments always stay greater than 0. So if I'm checking negative 11, x plus 3 greater than 0? Nope. So that means negative 11 doesn't work. So I don't even need to check the other argument there because it already failed. And then I'm going to check positive 1, x plus 3 greater than 0, because that's the first argument of our log. And that's a yes. Is x plus 7 greater than 0? 1 plus 7 is 8. Yes. So the only solution is positive 1. I'm going to leave you guys to try G. It's the same type of setup as what I just did. except I'll get you started on the first step. This is subtraction between these, so when you combine them, it makes a fraction. So you still have to do 3 to the 4th equals all of that stuff in the parentheses, but you have to start out with combining the logs first. Okay, I received just a couple more questions. Number 9 was one of those. So for number 9, we are doing long division, so I'm just going to do one of these. I'll do the first one. The reason we have to do long division is because what we're dividing by is bigger than x to the first power. So remember, you put what you're dividing by out front. You make sure you're not missing any powers. We actually are. We're missing x squared. So anytime you're missing a power, we put in a placeholder. We ask ourselves, what do you multiply 2x by to make 4x to the 4th? We'd need a 2 and an x squared. You multiply this by everything out front, so that would be 4x to the 4th plus 2. Oh, we need to put that under the correct term. That's why you want the like terms lined up. That's going to be a 2x squared. So that'll go right here. And then because we're doing long division, you have to change the signs. So this will be a negative and a negative. So this would cancel out. We would still have to bring down the 6x cubed. This would be negative 2x squared plus 3x and minus 1. So those all come down. Then we ask, how does 2x squared become 6x cubed? We would multiply by a positive 3 and an x to the first power. So if we multiply that by everything out front, that would be 6x to the third plus 3x. We need to change the signs. That cancels, and actually so does that, because they're opposites. So I'm only left with negative 2x squared and negative 1. What do you multiply negative or 2x squared by to make negative 2x squared? You use a negative 1. So we multiply that by everything out front and change the signs, and actually you get a remainder of 0. So this one has a quotient of 2x squared plus 3x minus 1 and a remainder of 0. So similar process to do part B. And then for number 11, I'll do one of these. I'll do the one that's already factored. All you have to do on B part is to factor it first. So we find our x-intercepts because we're trying to graph a polynomial. So our x-intercepts are negative 4, positive 3, and negative 1. You put those on a number line to figure out what's going to happen on each side, just like when we did test values for inequalities before. We pick test values in each region. We plug them into the individual factors. And what's going to happen is that when we find our signs, it's going to tell us, the overall sign will tell us if our graph is above the x-axis or below, because it's a y value. So it's actually going to tell us if we're up or down. So this would be negative, negative, negative. 3 negatives overall make a negative. This would be a positive, a negative, and a negative. That's an overall positive. And let's do squares around the positives. And then this would be positive, negative, positive, which is an overall negative. And then we would have positive, 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 which is an overall positive. Any of the pluses mean that we are above the x-axis. The minuses mean we are below the x-axis. Okay, so on a graph, this would look like this. You plot those x-intercepts. So 1, 2, 3, 4, that's negative 4, negative 1, and positive 3. And this graph, actually, if you think about your dots being here, this tells you what to do on each side. So we're negative on the left side of this dot, so that means we're down. We're up on the right side of that dot. We have to head back towards the second x-intercept. We're going to go down, and we'll eventually head back up, and we go up. So if we went down again, we would have to bounce and come back down. But ours went to positive at the end. So this would be the graph. And then there is the question, what is f of x is greater than 0 and when is f of x less than 0? That's related to these intervals. So I'm negative from negative infinity to negative 4 and from negative 1 to 3. I was positive from negative 4 to negative 1 and from 3 to infinity. So that's how you graph and answer the questions for these. And those are the, I believe, only questions I received so far. So hopefully that will help people who are studying for their exam.